Alrighty, guys, my name is Wyatt, and today we are going to be going over the experiment 3, which is the refrigeration cycle. Just some quick objectives here. We want to understand exactly how the refrigeration cycle works. Again, just kind of revisit that. Kind of forgot. Uh, the main results we're looking to get here is the coefficient of performance. We can do that by looking at the ideal and the actual values from the results of the previous lab. One very quick thing we can do is also measure the electric power into the condenser. Another important thing we really want to do is understand the pH diagram and describe how it works, both ideal and actual cases. This is the unit we were using. So these are just a few components, really important components that we needed to use. We got the compressor right there. On the left, you've got the condenser, you've got the water reservoir. You've got the two water pumps right there. They both connect to the condenser and the evaporator. And another important component we're using here is the expansion valve. We'll talk about that a little bit later on. So this is just to set up a list of all the components in our entire system here. All the SP values are the pressure inlets, pressure outlet sensors. ST values are the temperature inlet and temperature outlet sensors. But these are the main ones we're going to be focused on right there, circled in red. The SW1 is our compressor. Like I said, all the SPs, STs are your sensors. So that's really what we're going to be using on it, and we'll get those results from those sensors. So this is just going over the pH diagram and exactly how it works, the different states involved as soon as it goes through the compressor and all the other components. Whenever we go from state 1 to 2 in the compressor, we're putting work in. So you're going from the first state to the second state, which would be isentropic compression. You're not going to have any change in entropy. You're just going to be increasing the pressure. So when we go from states 2 to 3, you're going to be getting rid of heat from the condenser. The pressure is going to remain constant. So whenever you go from states 3 to 4, we're going through the expansion valve. This is just going to be decreasing the pressure mainly. So it's adiabatic, we can say. So whenever we go from states 4 to 1, we're also going to be removing heat from the evaporator. It's going to be constant pressure again. It's still going to be considered a superheated vapor. So this is the THC expansion valve. Basically what it does is it controls how much flow goes in and how much flow comes out. So whenever, if there's not enough, if the pressure isn't low enough, I guess, going to the evaporator, then it's going to turn on. If it's just enough, it's going to turn off. So how it works, whenever it comes in through the inlet, it's coming from the condenser at a higher pressure, probably a liquid. So whenever it goes through there, it goes through where the point P3 is right there, and that little spring is going to adjust how much comes in and how much goes out. So whenever it goes through the part 4 where the outlet is to the evaporator, it's going to become a low pressure, and it's going to be a vapor and liquid mix. So the Sensen bulb is really the key in determining how all this works. So since the system is adiabatic, we can say that the enthalpy at state 3 is equal to the enthalpy at state 4. So just a little bit of the procedure here before we're moving forward. We need to start the software as always. We're going to switch on both the water pumps. We're going to connect it to the evaporator and the condenser. So whenever we turn the compressor on the software on the computer, you're going to adjust that dial to roughly 40%. You don't want to go past that, or else we'll get inaccurate data. So whenever we adjust all of our flow rates, it'll only be on the evaporator side. So for the theoretical case, we did it at 5 liters per minute. I'm pretty sure I got those values, and we're going to compare them to the case 1, case 2, and case 3. We're going to be varying that from 6 liters per minute to 3 liters per minute. So after we do all that, well, first we need to let the system stabilize at each of those cases. Then we're going to record our data. So these are just some of the equations we're going to be using here mainly. The heat pump and the refrigerator cycle is basically the same thing. The only thing that's different are the hot and cold values you're mainly focusing on. So the coefficient of performance for the heat pump is the temperature of the hot over temperature of the hot minus temperature of the cold. Refrigerator is vice versa. So these are the ideal cases. So if we want the actual cases, which we'll mainly be focusing on, it will be the Q over the work value. That Q becomes MCP delta T. But we can write this in the change of entropy relations, which would be the H3 minus H2 over H2 minus H1 for the heat pump and vice versa for the refrigeration. So for the theoretical case, we set it to 5 liters per minute, and we were able to measure the compressor power right there at SW1. So if we want to get the ideal refrigeration values of the COP, we took the temperature from the evaporator and the temperature from the condenser. We can say that the temperature from the condenser is our lower cold value, and the temperature from the evaporator is our higher end value. So we did the low temperature of the low over temperature of the hot minus temperature of the low, which gave us a rough value of roughly 5.63. So now this is the value we were looking for earlier, the power from the condenser. This is given to us. You can also solve for it by enthalpy. I believe it's state 2 minus state 1 will give you the power. So if we want to get the actual heat pump, the coefficient of performance, we need to find m dot, which is just Q times density. It gave us that value. And then we need to find the Q gen value, which is the MCP delta T. And then we can finally do the Q gen over the work, which gave us a value of roughly 3.3. So this is our first case. As you can see, we had a pH diagram. We had to interpolate roughly double interpolate a few times for enthalpies. It was not fun at all. So as you can see, for the ideal and actual cases, they're roughly the same, except for at state 2, and this makes sense. So whenever you see on the pH diagram, you see the ideal and actual, they're roughly the same pretty much. So whenever we calculated the heat pump coefficient of performance, we did H3, enthalpy at 3 minus enthalpy of 2 over enthalpy of H2 over enthalpy of H1. So that gave us a value of 7.71. So for the refrigeration, however, we did H1 over H4 divided by H2 minus H1. That gave us 6.71. Now all these values should be really consistent. So we had 7.71 and 6.71. So the next one, they're probably going to be the same. You had the same, roughly same decimal place numbers and everything. So for case 2, we did this at 4.5 liters per minute. Definitely an uncertainty here. The data we got was only 4 liters per minute. So that can be an issue. I guess it doesn't have to be perfect how you adjust it. Just the numbers might be slightly different compared to other lab sections data probably. So same thing here. You got the coefficient of performance for the heat pump, which is 7.91, for the refrigeration cycle, which is 6.91. Same thing for case 3 we're doing. We found our enthalpies, put the pH diagram there. We found our coefficient of performance for the heat pump to be 6.81, and for the refrigeration was 5.81. So these are my resources. And I guess if you have any questions, just leave them in YouTube comments below.